Hi, everybody. I'm Janez Ales. I work at BASF, and my history is a mathematician who has all the degrees in algebraic or algorithmic graph theory. I had the lucky start that I have coded my first graph backend in 1987 for an NP-complete problem of Hamilton cycles on cubic graphs, and I never looked back since. So at the moment, I'm working at BASF, and we are dealing with a knowledge graph that is fairly big. At least 2 years ago, when I built it first, was cutting edge, 5 billion nodes, and 50 billion relationships, and counting. So I would like to talk about this as a basis to our future enterprise knowledge graph. So let's see, what do we have in this graph? So what's in our graph? On top of it, we have an ontology, chemistry ontology with 37 million nodes and initially 270 million relationships. And you know that this already turns the red light on, and we will address this issue further down the road. The main data in this graph are world's literature, journals, and patents. Literature is confidential by contract because it's provided by an external provider. And of course, we have BASF reports. It's about 500,000 of them, which are, of course, confidential. On top of that, we have 67 million synonyms, which we annotate our documents on. And I will quickly skim through the first few slides because I have used them last year. If you want more details, you can check the presentation from last year. So here is the rough size, and I would just focus on the number of ontology concepts, as said, roughly 40 million, and edges, 45 billion edges. Now, this sounds like a big graph. However, if we think of every pair of ontology concepts and try to persist similarity for these two ontology concepts in the neostore, well, we are looking at 10,000 terabytes of floats. So as you can see, this is already a very expensive endeavor. How does our schema looks like? Well, we have an ontology top left, we have BASF reports bottom left, and we have literature top right and patents on the bottom right. They are connected with the annotations, and in the middle of them, our synonyms are sitting. Now, what can one do with a structure like that? You can do local, you can do global traversals. One of the first testing tasks was to produce a list of descendant ontology concepts for each of the ontology concepts, however, avoiding all those who have not been annotated, or better, avoiding all those who have no annotated descendants. In other words, pruning this graph. And this is a local task is exponential, so it's a good test. And this runs in 30 minutes on a 128 CPU machine, and the machine has 2 terabytes of memory. Now, this is slightly misleading because the stage that communicates with neostore the most is getting all the children out. And this takes 10 minutes on any subsequent run, but the first. The first run is warming up the cache, as we know. And as we don't have any other mechanism to pre-warm the cache, then run the query. You have to fire it once, and that takes, the first time it takes 1 hour. The next task would be to persist depths of each ontology concept in this graph in the neostore. And this turned out to be an exercise in parallelization. First of all, one would want to use a periodic iterate, and that unfortunately at this scale didn't work, because at 40 million, one would split the batches into roughly 1 million, and after 40 million of transactions, this runs out of transaction space. Not to mention that each batch took 4 minutes to run. So when I took matters in my own hands and embedded Neo4j Enterprise into my Java project, fired off a server of that from my code, I was able to avoid wrapping up things into transactions. And I was big transactions, and I was only working with small transactions and able to persist these almost 40 million properties in 120 seconds. Now, this was more than a year ago, and if you follow the talks in the graph community, various different graph backhands, the companies are claiming things like, oh, we can persist 1 million properties in half a minute in a otherwise billion-size graph, and this is fairly recent. So you can see that this timing actually was fairly good already a year and a half ago when it was first made. I mentioned the problem of quadratic. Anything we do at scale needs to be n log n. As soon as you have n log to the power k of n, you're in trouble because that k will blow up into your face. So what do we want to do first? Well, we have plenty of author instances, but we don't know which person do they actually belong to. So let's look at an image of the BASF reports. In the middle, we have a meta node. All the blue nodes are instances of authors with exactly the same name. And here we group them according to the departmental, or if you want to look in the literature, according to the organizational signal. So the pink nodes are meta nodes for organizations or departments in this case, and the green nodes are the departments. Now, if you think that comparing two author names in terms of string comparison is complex because of the variability of author names, then you want to think twice and compare the organizational names, which are by far more complex and distant, and yet can show up as the same actual organization. Some journals include the addresses, and as soon as you include the addresses, the variability is huge. You may have departments listed, etc., etc. These are minor problems, but they're not really graph problems. Yes. So here is an example of this when we fan out from one meta organizational unit. So I would skim through that. We have a lot of other interesting things to discuss. As an overview, we have 555 million authors in total. This includes patent authors and journal authors and report authors. And we want to solve two problems, the homonym problem and the synonym problem. And if you want to match them, name them with cute names, the meta authors are solving your homonym problem. You need to partition the instances with the same string according to the persons that they actually belong to. And you want to extend that to the synonym problem. Those are the fuzzy authors, so the fuzzy matches to the meta author string. So we need to combine these two strategies, and we can do that in real time. Now, first we need to find an entry point into the graph, and that's done by building an index over the meta nodes. So when the user types a name, we can respond with a list of fuzzy matches. You can see if the input was XYZ Schwarz, then a match would also be, the fuzzy match would also be Schwarz XYZ, X point Schwarz, X dot Schwarz, and so on with dropping scores. Of course, you need to cut this off at some point and then produce the similarity partition. To skip over the trivial signals, which are like cited by and organizational signal that I've already mentioned, let's go straight into the ontology concept similarity, which is a lot more involved, and it's not a given that one can actually compute it given any ontology. Namely, ontology needs to be particularly nice. And if you look into the literature and some blogging from Neo4j members, you will see 10-node examples of DAGs as an ontology, which are instantly converted into a tree, and therefore avoiding any kind of problems that I'm going to be discussing now. However, the reality is a lot different. You cannot just put a spanning tree on your ontology and think that you've encompassed all the information that's been present before. So let's look at the use case here. In red, we have document nodes, and blue on top in the left picture is the root of the ontology. And you can see that ontology concepts that cover and describe these two documents on the left have a very big intersection. And therefore, the document similarity measured with a nonlinear similarity is 0.65, which is fairly high because at 0.3, the similarity is already fairly good. Remember, I mentioned that it's nonlinear. Yeah, so the 0.5 classic cutoff is not your friend here, but it's quite a bit lower. Now, these two documents belong to the same person, and obviously they are from the same area of expertise. But on the right side, we have an example, again, for the same person, two documents. However, they do not come from the same theme of this person's work. So when this signal is strong, it's a sufficient condition for these two instances belonging to the same person. However, it's not a necessary condition because the person can work on more than one project, different topic, I guess, one say. Now here, I would just point out on the bottom right, we have a complete list of the similarities, and you can see what I mentioned before. Yes, that 0.3 is already fairly high, and this is all I would talk about today. If you want more detail, as said, look up my last year's presentation. So here's an example of a cited by index. Remember, we do have two instances of authors here that have the same name. Yeah, so that's conditional probability. And if two documents which have the same author name in the author list have cited by relationships in between, there is a very, very high chance that these two instances belong to the same person. This is because authors like to cite themselves. So that's a no-brainer. Organizational signal is not that much harder, and I would wrap up with overview of what we need. We need a search index to find an entry point. We do a local traversal, and this is fast on the graph. You cannot do this in RDBMS of this size. It will just not come back. Local traversals in a graph are fast, and still, well, depending on which graph backend you use, some are faster, some are slower, some are better for this, some are better for that. But in general, a lot faster than any RDBMS systems. And there are signals that are very cheap to compute, and they could be calculated on the fly. However, when you have a limitation with one of them, that takes time to calculate, in this case, the ontology concept similarity, then you may be better off persisting all of them. So here is an image of a partition of similar name than x.schwarz into, so these are all the yellow instances are authors with the same string name. With the data that we bought, we also have an author ID that produces this partition. What we want is is we want to produce our own ID. Why? Well, the author ID is only available for about 70% of the literature authors. Yeah, so this is for less than 200 million instances in our 555 million author set. Plus, it doesn't contain any references to chemistry ontology and things like that, which is of course important when you're looking at a chemical company. So that's the core reason why we want to produce our own. And so here, the image now shows instances with the same name, but not necessarily the same person. And I have applied here cited by index similarity and the co-author similarity. And these are a given. Once you have a non-zero signal, you believe it. It's a 1. And then we have an organization signal. That's a continuous signal for every 2 paths. So you have to cut it off. And the same with the ontology concept. So here's a partition. And this is a known set. And we know which ones are the same person and which are different persons. Of course, we would like to do this for the whole data set. So how big actually this is, oops, sorry. Shows the following slide. So we have, for journal authors, we have 360 million of them and 67 million meta nodes. So that means 67 million distinct string names. And top right, you can see the matrix. It's of course not complete. The blocks on the diagonal are the homonym problem, and the close by blocks to the diagonal are solving your synonym problem. And to be able to do this on the fly for a particular name is possible, as I said. But if you don't have complicated signals, and we have one that's complicated enough, and this complicated needs to be understood with the data. It depends on the data, and see why. So we have an entry point into the graph, and we can do these hops fairly quickly, like 10 milliseconds or so. And we do the fuzzy match through the index lookup, and we wrap around here. This arrow points and comes around on the right side of the slide. So we ultimately end up with 2 sets of ontology concepts, and we want to find out how similar they are. You can't be pre-computing that. You can be pre-computing for every pair of ontology concepts, maybe, as I said, a huge disk footprint in terms of memory. So we are dealing with this on the fly. And can we do it? Well, imagine one ontology concept. How many paths to the top, to the ontology root, does this ontology concept have? If our ontology is a tree, there is only one. Excellent. However, in our current ontology, we have 7 times as many edges as there are nodes. And you will all know that that is not even close to a tree. Now, every time you go 1 plus 1 on this factor, your number of paths explodes. Imagine you only have twice the number of edges as there are nodes. Well, you could have that on a path of length 10. So at every step, you're allowed to choose one or the other edge. Voila, it's already exploded, right? So that's your problem. You have n paths from one ontology concept to the top, to the root, and you have k for the other one, and you need to be finding the least common predecessor. This is, of course, very fast when you have a tree for your ontology. If you don't have a tree, this eventually blows up. And I predicted this before I even hit on this example. So yeah, it's not a miracle that this has happened. What we need to do is we need to unload the overloaded relationship, which is only one in our ontology. And that's one of the future steps that we need to do. So let's look at the two pipelines that I had to build in order to be able to execute this. This one is getting the data into Neo4j. So the textual data was prepared well with unique IDs. The trouble was that some of these IDs, in order to make them unique, the external provider made them 80 characters long. Of course, that's way too long. And we needed to map this into long integer IDs here in the middle orange block. And that was 2 years ago done with Python via the Kiwi library and the Kiwi dictionary. The min load was taking 2.5 days in 358. We hit a problem of 4 bugs plus time blow up on the load up to 11 days, and you can see that was painful and to debug many cycles of that. Pretty much 6 weeks ago, we solved it with a custom Docker that's going to be released apparently today, I think, in a 4.3 version. So this is now back on track. The neostore is 7 terabytes big. So you need some good disks also attached to your machine. And let's look at the pipeline that executes traversal code. So we have a Java embedded Neo4j project, and to make that feasible, of course, you need a build tool. Remember, there's about 5,000 jar files that are in the dependency of my Java project. And this runs on a 128 CPU machine with 2 terabytes of RAM, and the disk is needs about 20 terabytes to be able to run one pipeline. Definitely with a 32, I can't squeeze 2 pipelines in, one operational, one in development. So then my traversals can be triggered via a Cypress shell or a web browser or however you want to access my server. Now, as a basis of a BASF knowledge graph, this graph is a pretty good candidate. However, to actually achieve the realization of an enterprise graph, one needs a top-down approval. Well, with the lack of that, one needs to build a community that will realize how useful these things are, and this is what we have been doing lately. Somehow we had to switch from focusing onto R&D community to the business impact project, and here are 2 examples that I have a few slides to show. So this is from the enterprise architecture department, who's interested. They are interested in cutting costs with applications that we pay for but nobody's using in extreme case, or similar applications where we're paying overall licenses for more than one, but we could be only doing for one. So thank you. This image shows a department node in the center and 6 applications that this department is using, or I guess maybe there are 7. In any case, in the red, we have the resources spread around, whether they're hardware or software, around BASF. So if I tell you that the structures on the red nodes are trees, would you believe me? I'm not so sure, but I can prove that to you. So let's look at this one here. And we see, voila, indeed, these are trees. And if we had more time, I would ask a $100 million question here. Does anybody see a problem with this data? So actually, at the first sight, there is a problem. Most red nodes have a green counterpart. But for example, here on the left, that's not the case. Well, these are resources that the first one is used by the application that I've fanned out from. However, they are also shared with other applications. So if I actually add a second app ID from the right here in my description, symbolic description of the query, we actually see, yes, these are the trees, and they provide a very rich context in which to explore the relationships between different applications. What did we lose here? The green nodes now don't represent only one application, but many, and let's see how many. If I add the meta nodes and contract, we can see in dark green are the meta nodes for applications, and there's about 10 of them. What this image is telling you is which resources are shared between different applications. You can see a simple tree structure, and yet when you view it from various different angles, you get answers to various different questions. So I'll stop with this example, and I have another one. Another department is responsible for norms and their dependencies and their updating. So when a request comes that the norm has changed, all the dependent norms also have to change. I don't want to go into a detail showing of the one similar case, one simple example, but you can imagine. So far, the tool was input the norm, get out the list of dependent norms. And then the person needs to do that over and over again for each of the hits. And so that is essentially a DAG that you create into your spreadsheet. And after 4 hops, you're pretty much done and crazy. So a graph does that with one simple query. And let's see the data set now in the blue view. You can see that there are some norms that have pairwise many dependencies between them recorded inside the documents. And if I scroll through, here we already see that there's somehow non-uniform distributions of different types of dependencies. That's correct. This is not a complete data set. It was just a sample data set crafted by a human from the norms that they have been using in their past, right? So if I scroll to the end, this is the data set. This is the data set that we have now. And if we zoom in, we can already see a nice view of dependencies and how, starting from one particular node, you can do 1 hop traversals, 2 hop traversals, fan outs, 3, 4, and so on, in order to produce the lists of people responsible for updating these norms with, of course, norm names, which would save a lot of time to somebody sitting and having to do this work. Remember, changes are coming on a daily basis. So I've given a couple of use cases. We have another half a dozen that we are working on, and half a dozen that people are ready and eager to use our knowledge graph expertise. So we have plenty of work to do in the future. Thank you very much.